Hello YouTube, De-bodgery here, aka Richard Gumfaw on Facebook. Can't get out of this thing without doing a macro lens video, at least one, right? The BAC8000, and the daughter board is probably the most interesting thing here. The main board, there's some little parts on there that we can look at up close, but that one will be much harder to do, because the backside of the board is covered with MOSFETs, and, well, it's not quite as stable as this little daughter board is, so I think I'm going to forego that one, and there's not a whole lot of interest there to look at, so, yeah, and a lot of that stuff is occluded by all the capacitors on there, so it's much harder to do than the daughter board. Anyway, you are looking at the TMS 320, which is the processor for this controller, and that's a TI chip. It's more or less comparable to an STM32, like might be used on something that's VESP based, say like the like the Trampa 100-250, or even like say the EBMX 9000 controller is also VESP based and would use one of the more advanced STM32 processors. Whereas this is a TMS TI chip. And I believe, and I could be wrong, someone feel free to correct me, I have not done any research whatsoever into the TMS 320, so I know only a little bit about it, but I believe that this chip was deliberately designed for FOC motor control in mind. I know that it has some kind of a math processor built into it, and field-oriented control does require a fair bit of on-the-fly calculation, and so having a little bit of a math processor in there would be useful, and I don't believe that's the case for the STM32 processors. I believe that they are completely software driven, so not quite as optimized as the TMS 320 would be. But anyway, yeah, they still are both got the capability of the full FOC functionality suite in them. It's just that maybe the TMS 320 is a little bit better at it than is the STM32s. So, in looking at this board a little bit more, I believe that this little MOSFET right here, which there was a few minutes in time where I thought maybe that was a 3.3 volt regulator, but it is not. That is a MOSFET. I believe that this little guy right here is the enable, if you will. It's what applies battery plus voltage. Pretty sure this is the case to this little DC to DC right there. So this is a common way that controllers are so-called enabled. It's really powering up the CPU is what's going on. And so this little DC to DC, so here's the inductor, you've got some ceramic capacitors for ripple filtering, and then you've got a little control chip which has got a MOSFET in it and a few other components like an oscillator and so on to be able to create a proper DC to DC buck converter. And so battery voltage comes in, and like say 3.3 volts comes out, and that's your enable per se. And probably and actually that's probably not 3.3 volts now that I think about it. It's probably something else, like say 12 volts. But I also know that the Bluetooth module and the TMS 320 need 3.3 volts, so I don't know how that's done. Haven't figured that part out on here. But yeah, I'm pretty sure that little DC to DC is either making 3.3 volts or it's making like 12 volts, and I don't know which it is. And I probably never will. But 3.3 makes sense because the Bluetooth module and this little chip both need 3.3 volts. So that seems likely. This other couple of chips down here, so those two guys, they probably need 5 volts. And in fact, right there, that is a 7805, which is a 5 volt regulator. So probably that little linear regulator is to provide power for these guys. And it would not be able to do that off of a 3.3 volt source, say from that little DC to DC converter on the other side. So there's where my questions come in. Don't know where the 3.3 volts are coming from. which makes me think that that little DC to DC is 3.3 volts, but then there's not another DC to DC here. So how is this thing getting, say, like it's 7 or 8 volts input that it needs to be able to make 5 volts out? So there's some things there that I don't understand how that works. But yeah. Anyway, I'm sure it's all in the schematics, and if I was looking at them, it would become abundantly obvious. So I'm just making guesses based on circuit layouts and parts and placements and things. This is an interesting little piece right here. This is a little tiny isolation transformer, and it appears to feed into that chip right there. So most likely on this side over here, and you've got a couple of resistors on there, most likely on this side you have, say, back EMF maybe, or you've got battery voltage. You've got something AC, let's just call it that, because that's a transformer, so it doesn't really do DC very well. But anyway, yeah, this little transformer is basically isolating the high voltage side from the low voltage side so that this little chip survives. Yeah, and those little resistors right there are kind of balancing both legs on the input side of that little transformer. But something on the high voltage side comes into here, gets isolated, and fed over to that little chip right there, and most likely that's some sort of a back EMF signal, something like that. Maybe that's part of like the inductance measuring circuitry, because FOC needs that. So that's very possible. I don't know. And yeah, you can see where I kind of buggered some parts right there. You can see a couple little, those are probably capacitors. I'm not really sure what they are, but I've oh wait, there we go. So that one says it's an inductor. That's what L means. And those ones, I'm kind of covering them up. I don't know what they are. Yeah, since these are all inductors, those are probably inductors too. But yeah, I had my spooger basically in here prying on the board gently while I was applying heat to those pins on the connector right there, getting the solder to melt so that I could pull this loose and, well, jiggered up some parts on there. That was a foregone conclusion that was going to happen, because this was going to be a destructive teardown. That was a foregone conclusion right up front. And sure enough, it was somewhat destructive. Yeah, if I didn't have to pull up the logic board, I probably could have saved that one some trouble. Let's look at this side of the board. So this I found a little odd. This was the first thing I noticed that I didn't like. So this little green board right here, this is the Bluetooth module. And as you can see, it's got these 4 little green wires that go down to 4 little solder pads there. And it's just a 1-for-1 pin for pin. So why ASI chose this rather than to solder the Bluetooth module directly down to here doesn't make a whole lot of sense to me. The little board was wrapped in some Kapton tape. You can see this spot right here where somebody put down a little piece of double-sided foam tape and then stuck the thing down. So don't know why they did that. Why not just take this little board and solder it right here instead? You wouldn't have to have wrapped it in Kapton. You wouldn't have needed the double-sided foam tape. It would have been the same thing. It's not going anywhere because all the stuff was coated in potting, so it wasn't going anywhere. But still, it's odd. You know, this is extra steps, and the solder work isn't that great. The amount of bare wire on the ends isn't awesome. Those are things that cause shorts. Yeah, this solder work is, well, not awesome. I could do better solder work than that, and have on smaller parts. Yeah. So anyway, scoot this over a bit more. There we go. I believe that these little pads right here are the programming port for the TPS 320. On most everything that's STM32, you will find something very similar to this, just a little array of pads, and yeah, you put the right connector on those things and press it down, and then you can load the hex file into the CPU, and ta-da, now it's live. It is common practice that boards like this are completely assembled, and then once they are, then you program the CPU after the fact, not before, because it's much harder to try to do it as a standalone chip rather than integrated onto a board where you just have access to the programming pins. So probably that's the programming port. That's highly probable. Right next to it, this is the LED that shines through the light pipe, and you can see through the top cover. The junk around it is silicone. I kind of dug at it a little bit trying to get that off the board, but I was going to start lifting parts, so I stopped. Anyway, it was much nicer before I started digging at it, and I'm pretty sure that silicone is there to protect this LED from getting potting on it, because, well, the potting is opaque, and the LED needs to shine through that light pipe. So I think that's what that was about. I've already mentioned this little DC to DC. Don't know if that produces 3.3 volts or it produces 12 volts. Haven't decided on that. I don't see a 3.3 volt regulator on here anywhere, so I can't say what that is. There's this interesting little 5-pin chip here. I don't know what that does either. Haven't looked up any of these part numbers, and a lot of times little things like this, they'll have like a 3-digit number on it, and you can look and look and look and you won't find the parts. Another little 6-pin chip there. Don't know what that does. You know, a bunch of little, like there's a little MOSFET. You've got a little full-wave bridge rectifier right there. I don't know what that does, but something AC needs to be brought in as DC is my guess. Don't know why. Yeah, you've got a bunch of little inductors on here, looks like. Maybe some resistors. Yeah, most of those say L, not D, not R. So little inductors on there. So they are probably some or other filtering for AC in some way, AC signals, and hence the need for inductors. Anyway, there we go. There is the logic board. There's just one other connector over here I wanted to explore a little bit. So you see this little guy right here, and I believe that's the UART on the TPS 320. So I believe it says TX and RX on there. Let me pull that away and look at it under much higher magnification. See what I can see on there, because it does have, yeah. So it says ground clock 3.3 volts and DIO. So that might actually be the programming port, not the other. Ground clock 3.3 volts and DIO, so digital IO. So it's a little serial port. That may be the equivalent. Yeah, there we go. Now it's focused on it. May be the equivalent of TX and RX, kind of a UART sort of a thing. I don't know. I don't know the TPS 320 chip like hardly at all, so I am speaking out my ass in regards to that chip. I'm guessing about certain things, so maybe that's programming port, maybe that's the UART, something like that. I am just guessing. Anyway, hope that's interesting to some folks. It's certainly been a fun exploration for me. I have learned more about ASI controllers in the last couple of hours than I have known in the previous 3 or 4 years where I have used them and programmed them. Because I have never been able to do this before. So that's super cool. Take care, folks.